class was really good. So he made really good.
All right, did everyone get a copy? Cool. A few comments there before I get the actual lecture underway. Let's see what's on my list of things. We've got your labs and we've got your homeworks. I'm going to try to get both those back to you this week. So you'll have, I hope, a pretty good sense of where you stand in the class at that point. There's been different sort of emails in the class, sort of where you are grade-wise and stuff like this. It's a little hard to say right now until we get some more assignments back. But I'll give you some sense of an update once we get back the second homework assignment in the lab, and then you'll sort of know where you stand relative to the class, and then we can, as needed, talk about other options. I'm glad you guys, many of you took advantage of sort of the regrade option. I think that's a good way to pick up all the material that you didn't sort of catch the first time through, so I think that worked well. Don't expect to do that for the second homework assignment, just so you know. What else is going on? We've got homework 3 that's going to come out today. I just need to review the assignment quickly, and then I'll post it sometime this afternoon or this evening, maybe late tonight. But that'll be available, and then you've got roughly a week and a half to work on that as well. And then it's a little bit further out before we get to the next lab and the final assignment, which you can keep those things in mind. The other thing I wanted to get some feedback from, I sent an email about this, and several of you got back to me, but I've had a request to move this class next year from 1 to 3 to 2 to 4. And the thing I'm most concerned about is whether that would actually overlap with a class that you're already taking. Seems unlikely, but I guess it's possible. So would that cause a problem for anyone? I think it's generally maybe not preferred, but okay. So by show of hands, it's not a problem per se. And then by show of hands, can you raise your hand if you prefer it being 1 to 3? And then does anyone prefer it at 2 to 4? Okay. I'm just trying to get a sense, right? Because these things are hard to move around, and then when you do, it's hard to go back and whatnot. But there's another professor that's teaching a class, and for some reason he wants to move his time, so that he's asking me if I can move my time. But try to figure out what this means, right? Okay. At any rate, thanks for that. With that, I think go ahead and get sort of underway here. I like this lecture a lot. This is a little bit of a longish one in that we have more work to do on the board than we have for some of the previous lectures. And so if you thought it was a lot before, we got more today. But I think personally, I think this is a really neat lecture because I want to try to make the connection for you guys today between the transverse magnetization and K-space. How is it that we've talked about Faraday's law of induction and kind of wave our hands, we've got gradients, there's K-space, and I want to try to delve into how it is that the state of the transverse magnetization is detected and all the various signal processing steps that get us to the point where we can assign a value to a point in K-space, okay? And that's obviously critical to how MR works because we do all of the imaging principally in the Fourier domain. So we really need to understand this connection. This is the lecture that in principle ties those sort of concepts together, but it will require that we do. With that, I'll go ahead and get started unless there's sort of questions about sort of where we are in the class or things that we're doing. I think the assignment plan is pretty straightforward at this point. We'll have a good lab for you guys. So what we're here to talk about today is a signal equation. You've actually seen this a little bit at the end of Holden's lecture, and there was some discussion of it in Kyung's lectures as well. But we're going to back up a little bit and work through some of this material again today. At the end of Kyung's lecture, you started seeing expressions like this that told us that there was a signal, a time-varying signal that could be picked up in our coil. And the evidence here that you're picking up something in your coil is that you're integrating the response of all of your transverse magnetization over all dx and all dy. And so at a specific point in time, you're getting signal from the entire slice, but that signal's been spatially encoded for a particular spatial frequency, and that ultimately gives you data that you can assign to a point in K-space. These aren't easy concepts to understand, but we're going to drill into it some more today. And the idea is that we have some state of our transverse magnetization, and we know a fair bit about how to manipulate the transverse magnetization. We learned about saturation pulses, we learned about inversion pulses, we learned about gradient echoes, we learned about spin echoes. And these are all ways, either through the timing of the inversion pulse, or the TE we choose, or the TR that we choose, that set up a state of transverse magnetization. It depends on the precise location we're talking about, the X and Y coordinates, because every X and Y coordinate has its own, not necessarily unique, but has its own T1s and T2s and proton densities, for example. And these things, of course, change as a function of time because everything's trying to relax back towards equilibrium. And the part here that we want to build on some insight today, and we'll talk about it again in the next lecture, is the second term here. And this is the spatial frequency encoding term, right? This is an exponential, a complex exponential term that, through the application of some gradients, either an X gradient or a Y gradient or the combination of the two, sets up a pattern in our magnetization that has a specific spatial frequency. We can talk about having high spatial frequencies, or we can talk about having low, slow-changing spatial frequencies. But every object is comprised of the appropriate balance of different spatial frequencies. And ultimately, what this signal equation tells us is what is the magnitude of the state of our magnetization for a particular spatial frequency, and really at a particular point in time. And we're going to learn today how we make the connection between gradients, time, and k-space. You saw it some already in the expressions that are shown down here below. And so we can see that the k point, so kx and ky are just different points in k-space, where if kx is 0 and ky is 0, we're at the middle of k-space. And as those spatial frequencies become higher and higher and higher, we can move out towards the edges of k-space. And where we are in k-space at a particular point in time depends on the magnitude of the applied gradient and the duration, or the time for which that gradient has been applied. And it's the same, not surprisingly, for kx and for ky, the difference being whether you're applying the gx gradient or you're applying the gy gradient. So we'll come back to these expressions and this top expression today to try to give it a little bit more, give you a little bit more insight about it. There were some real practical outcomes that came out of that lecture as well that are important to know and sometimes difficult to have an intuition for. But the bottom line is both of these expressions are really important in MR because we care a lot about our field of view. Our field of view restricts, in some sense, the part of the object that we're going to be imaging. And we need to choose our field of view appropriately, and that seems easy enough because, at least on the scanner, it's just drawing the box around the thing we care about. But behind the scenes, it's important to understand that how we change the field of view is governed by the delta kx or the delta ky. What's our jump in k-space when we're collecting points in k-space? And that, I think, is actually a very difficult thing to have an intuition for, but fortunately the expression is relatively straightforward. So I would highlight that you'll work with this in the third homework assignment, but you'll also want to keep that in mind sort of moving forward generally. We also know that while k-space is related to the field of view, k-space is also related to the underlying spatial resolution. So there's slightly different ways of making, expressing this, but probably the most straightforward one is shown here on the bottom, that the delta x that you can resolve, which is basically like the pixel width, if you will, is related to 1 over the number of readout points. So we can talk about how many points we actually make a measurement for, and then the underlying delta kx as well. And so the product of these things, or 1 over their product, defines our spatial resolution. On the scanner, we usually nominate or choose our spatial resolution, and then and we may, in fact, or typically choose the number of readout points as well. And that means the scanner's left to pick one free variable, which is delta kx. It'd be confusing if we had to think in terms of delta kx's. So I want to point out the relationship, but then we work with free parameters to then determine the other through these equations. Yes?
So I'm just kind of confused from the last lecture, but the kx and ky, are they a result of the phase and frequency encoding, or are they separate?
Usually the way we break it down is we usually describe kx as being in the readout direction, which is like the fast acquisition direction, and ky is the phase encoding direction. It's the application of the phase encoding gradient followed by a frequency encoding gradient that specifies which k points we're actually measuring. So if that very first phase encode gradient, the ky gradient is 0, and then we turn on a readout gradient to get our kx points, we're going to get the kx points for ky equals 0. We can then turn on a ky gradient. We can move that line up in k-space and go to a line that's further and further out in k-space, depending on how long the ky gradient was turned on for. If it's turned on for longer, we can move out farther. And as we're moving out, we're getting higher and higher spatial frequency information. In particular, higher ky spatial frequency information. And the kx is still nominally the same. Does that help? Okay. Hopefully today we're going to tie some of this together. But fortunately, some of these expressions, the ones on the bottom there, are relatively easy to remember. Having an intuition for it is yet another thing. That's still not straightforward, in my opinion. Okay. So where are we in this sort of long sequence of possible events? Well, in the previous 2 lectures, we learned about spatial encoding, right? How do gradients help us specify things like resolution and field of view and where we are in k-space? What we're going to talk about today is we're going to go from having a state of transverse magnetization that's been spatially encoded. We know that there's some connection between this and a voltage that shows up in a coil, and then eventually some k-space signal. And today what we're going to do is talk about procedurally how the hardware takes us through these different steps. So that hopefully at the end of today you can understand what a point in k-space represents and how we get from spinning magnetization to a point in k-space. And it's a fair bit of work to do that, but hopefully in working through it procedurally you'll get some understanding. Okay, so that's our challenge for today. This stuff you guys know already, but just sort of for qualitative overview, we know that if we excite spins so that they have magnetization in the transverse plane, as they precess, they'll precess at the Larmor frequency, and that's going to be detectable in a nearby coil. And part of the trick was actually to turn on spatial encoding gradients so that we can get different frequencies as a function of space. And so here we've turned on, say, a Y gradient. I've got magnetization on the left-hand side precessing at one frequency. Magnetization in the middle has no apparent precession because we're in the rotating frame. And then when we go over to the right-hand side, the application of the gradient has caused those spins to speed up. So they're at an even higher Larmor frequency. If we want to image a slice that's on the right-hand side here, for example, we're going to detect in our nearby coil some flux, some voltage, and then through a series of events, turn that into a measured frequency, and maybe we get an oscillation that's shown in the green curve. We know if we move over to a different slice on the other side of the body, the precessional behavior is different. In this case, it's a negative frequency, or it's a same frequency with a phase shift. And so we expect that spins from, say, the left-hand side of the scanner, patient's left, or patient's right-hand side of the scanner, will give us things with similar frequencies, but there must be a difference in the phase, at least for the specific example I've shown here. If we wanted to, we could draw the flux that we would get, or the voltage signal we would get for this middle line here, and it would actually show up in this case as being very, very flat. It's still something we can detect because it's still precessing in the lab frame at 64 megahertz. This is just the example of the rotating frame where it draws out the differences in precessional frequency between, say, adjacent spins with the presence of an applied gradient. And then the steps that we'll talk about, we'll get to it really more tomorrow, Wednesday rather, is how we can use these signals, use a 2D Fourier transform, and then get ourselves to actually have a useful diagnostic image. Okay, so procedurally, this is what we're trying to get through today. We have an object, and I want to make a distinction between the object and the image, right? So the object is the thing that's actually lying in the scanner. And we can, through various, inversion pulses and choices in spin echo or gradient echo parameters, we can generate some transverse magnetization that's specific to every pixel location, every position. And that magnetization will change as a function of time. If nothing else, it's going to be relaxing back to equilibrium. And it's also going to be precessing at the Larmor frequency, right? So at least because I've said so thus far, and if you have some insight for Faraday's law of induction, then you would appreciate that this transverse magnetization can induce a voltage in some nearby coil. This voltage signal is going to be very high frequency, right? It's going to be a 64 megahertz signal. or at least that's the so-called carrier frequency. All the spins are nominally at 64 megahertz. The application of the gradient will give you some spectrum to that. Not everything at 64 megahertz, but pretty close, within, kilohertz or tens of kilohertz. And so then the trick is to go from a voltage signal to what we'll call, I guess at this point, it's like a baseband signal. We're going to talk about how we can take our voltage signal and get ourselves, this will be a complex signal that's been demodulated. I'll show you the steps. And then the next thing is to go from the signal that's a function of time, and then it's really a relatively simple substitution where we can talk about the signal that we acquired at a point in time should be in fact assigned to a particular point in k-space. And the transformation from an S of t signal to, say, an S of k signal depends on the gradients that were being applied at that particular point in time. And we'll work through that as well. So our goal today is to try to understand how we go from objects that have been encoded through voltage signals to this lower frequency signal, ultimately to a k-space signal. When we come back on Wednesday, we'll talk more about how and why the k-space signal itself ends up being sort of the 2D Fourier transform or inverse Fourier transform of the image. So we'll get to this point really more on Wednesday. Clear, at least procedurally, what we're trying to accomplish? Okay, it's a lot of steps, but we'll get there. Okay, so I think already we know how to prepare the transverse magnetization. You guys have some ideas. You've worked on homework problems. You've seen me do it in class. We know how to set up a state of magnetization that has inherent image contrast, differences between pixels. And we know a bit about spatial encoding. It's not solid yet. We've had a couple lectures, but it really takes much more than that for any of this to become, by any stretch, intuitive. And so the question really for us today is, how does that transverse magnetization get converted to k-space? And this will give us a little bit more insight to how the spatial encoding process works, and then Wednesday's lecture will give you a little bit more input as well. So this is the one way of sort of also drawing out the same sort of sequence of events. We know we need to put RF energy into our spin system so we can generate an interesting state of the transverse magnetization. T1 weighted, proton density weighted, whatever. We know, at least because we've been told several times, that transverse magnetization will generate a voltage in a nearby coil through Faraday's law of induction. What we're going to talk about more today is how we use what's called phase-sensitive detection to actually transform this voltage-based signal into a complex signal that's free of the precessional behavior. And so this transformation right here will actually be able to, when we go through these steps, we'll actually be able to have a complex signal. And that's interesting because it tells us where in the transverse plane the bulk magnetization lies. Not just that it's oscillating, but it's oscillating and has a particular phase at any given time. So it's a truly complex signal, but we'll also be demodulating or getting rid of that carrier frequency. The B0 Larmor frequency stuff is nice from a detection principle. You'll see how that shows up today. But in principle, we want to get rid of it because the interesting information for us is stored in the other frequencies, the frequencies that were generated through spatial encoding, application of spatial frequency encoding gradients. So we've got to get rid of the baseband signal. We know, we saw this a little bit already, how points in k-space are related to the applied gradients. This is, in this case, the frequency encoding gradient, and how long that gradient's been turned on for. There's some subtlety here about whether we're talking about FID signals on the top or echo-based signals on the bottom, but we'll get to that today as well. And then by effectively substituting the definition of K into this S of T signal, we'll get back to an S of K signal, so a signal that's a function of K-space. And that means that we know where to put the acquired data. We just measured something, we know something about its magnitude, we know something about its phase, and we know where it belongs in K-space because we know what gradients were being applied. So this is the decoding process. You have to know, and that's what this expression in the top right-hand corner is saying, you have to know what the applied gradients were to know where you are in K-space. It's not too surprising. We know gradients move us through K-space. If I know what the applied gradients are, then I should be able to tell myself where am I in K-space. Again, we'll work through this as well. So finally, we'll end up with points in K-space that come from ultimately this acquired voltage signal. And then, you're probably getting some sense for this already, but you'll get more of it. We can then just take the 2D-FT or fast Fourier transform with this K data to recover back an image of the underlying object. So again, making this distinction between the image and the object. Okay, so the first step is how do we go from the transverse magnetization to this voltage that we keep talking about? The first principle is just through Faraday's law of induction. So we know we have transverse magnetization, and we know that the time rate of change of some magnetic field flux is related to some voltage. So we have to figure out what's our flux. And our flux is in turn related to a couple things, including the state of our transverse magnetization. No transverse magnetization, no flux. More transverse magnetization, more flux. But it's also related to actually the coil that we're using. You can have a good coil and you can have a bad coil. This is a sort of a basic definition of flux where we can integrate the B field that's penetrating through some surface and thereby calculate some flux, and that B field would be say time varying. That gives us a little bit of intuition as to where it gives us some intuition as to where the flux term is coming from, but in something I don't really like to do, we're going to take a little bit of a leap of faith here in trying to understand fluxes in the context of MRI. And so the basic detection principle for MRI relies obviously on magnetic flux through that coil, and we describe it through principles of reciprocity. This is not something that I can really give you really good insight for, but I'll try to give you some intuition as to why the equation is meaningful. So here we're saying that the flux, the magnetic field flux, is a function of time. What you pick up in your coil, if you will, is dependent on integrating everything coming out of the object, right? We're sensitive just to what we've excited, whatever part, whatever slice of the object, whatever volume of the object, but our coil is in principle sensitive to all of it. And the flux that you'll pick up depends on two things. It depends on the state of the bulk magnetization, so that's not surprising. If I have more transverse magnetization, I should pick up more flux. If I have less transverse magnetization, I should pick up less flux. Note we're talking about the full bulk magnetization vector at this point. We're going to look at it component-wise and talk about terms that matter and terms that don't in just a second. The term I have to introduce here, and there are direct ways of sort of linking this back to the flux equation on the previous side, but we're going to skip that today and just introduce this concept of so-called coil sensitivity. We subscript it as R because that's usually the receiver. So this is the receiver's B field, if you will. And that's the part that's not maybe intuitive, but what it means is that the flux that we detect depends on the properties of the coil itself. We're going to have a larger B field, a larger effective B field if our coil is more sensitive, if somehow the electronics are tuned and made such that it's more sensitive to picking up fluxes. And if you have a less sensitive coil because you had crummy electronics and you built it poorly using cheap parts, then your overall sensitivity is going to be lower. So we get some sense that we can build good antennas and we can build bad antennas, right? And so you can think about it here. What happens if the coil has poor sensitivity? Well, obviously you're going to get poor flux and you'll get a weak signal relative to having a good coil. Okay, fine. Interestingly, what happens if the coil sensitivity is perpendicular to the bulk magnetization? So the bulk magnetization is in the transverse plane. The stuff that we detect, I keep saying, is in the transverse plane, right? What happens if I put a loop coil across the top of my head in the scanner? What's that, Kamal? Nothing. Why? Yeah, it's perpendicular, right? So my dot product doesn't give me anything useful, right? So obviously the orientation of your coil matters tremendously in MR, and all the coils are nominally going to be oriented to be perpendicular to the z-axis of the coil, if you will. So how would that happen? Well, it would basically happen if you inadvertently placed a coil in an unacceptable sort of configuration. Okay, so why am I mentioning all this? Well, what we want to do is try to understand how we can define the flux given the bulk magnetization and what we know and expect from the sensitivity of the receiver coil. And then we're going to differentiate that with respect to time to get back to a voltage. And this is what will tie together voltage signals that we record with the state of the transverse magnetization that we generated. We talk a little bit more about the coil sensitivity. Obviously, we've talked about its sensitivity, meaning how well does it pick up the state of the bulk magnetization. But in addition to having sensitivity, which could be a function of space, meaning you're sensitive to things that are really close to you, but you're probably less sensitive to things that are farther away. You can also have phase, meaning that coil itself can add phase to your signal because of the tuning of the electronics. Things aren't always perfect for all spatial positions. And so your receiver coil can add phase to your magnetic, to your signal as well. So you'll see how the magnitude and the phase enter in. We know we have lots of coils. I think I probably showed you a slide like this before, but we have, and you saw it when we were in the lab, but we have coils that are specific to every sort of anatomical region of interest. And we were just talking today about ordering a breast coil to get a breast imaging clinic going. We were talking about ordering a new head coil for specific procedures. So this is sort of bread and butter stuff for MR. You're going to have a bevy of possible coil choices that are going to be specific for the diagnostic task that you're chasing down. Just sort of qualitatively, I want to show you how this all sort of comes together. So let's say we're trying to image this particular subject. We might place what we call a coil anteriorly. We call it a chest coil or a body coil. So that coil itself usually has several channels in it. And so all of the sort of best systems right now are multi-channel systems. We're receiving with 8 channels or 16 or 32. There's head coils with 128 channels, meaning there are 128 individual coils all sensitive to detecting that MR signal. Needless to say, the position of the coil on the subject will govern the sensitivity that it has to the underlying tissues. And so if this coil is, this is a map of the coil's sensitivity, meaning that for an anatomical image that would be acquired for this top coil, coil 1, it's going to be most sensitive to things that are in this corner and less sensitive as things get farther and farther away from the position of the coil. So the labeling is maybe a little bit confusing. This is the image or the sensitivity that coil 1 has across the field of view. And you'll see that the sensitivity that coil 2 has across the field of view is similar but distinct. And it's distinct because the position of coil 2 is different. Coil 2 we take to be this lower coil. We can put coils on the back as well, and we'll get different sensitivity profiles. The coil performance itself are all very, very similar, but because they're located in different geometric positions, they have different sensitivity across the field of view. And they're most sensitive to the part of the field of view that's closest to the coil. So the coil element itself is going to be sort of in this corner, or in this corner, or in this corner, or in this corner. So individual coils like this, relatively small coils, they don't have good sensitivity over the entire field of view, and in a sense that's a bad thing. It turns out there's some advantages to this as well. Pick up less noise. A lot of our noise is so-called body noise. It's noise coming from the subject themselves. It's not electronic noise, is almost entirely dealt with. So at any rate, the coils have different sensitivities. If I acquired an image with each individual coil and reconstructed it, I would really just get insight or sort of conspicuity for different parts of my field of view. We'll talk about this more in maybe the very end of this lecture and then more on Wednesday as well. But the basic idea is that we just need to composite information. Oh, I didn't put it in there. We can basically do a square root sum of the squares of these different images to composite an image that's more uniform in its appearance. It's a very standard thing to do. But you might be doing this with 32 coils or 16 coils or whatever, sometimes called channels. So it's a little confusing, the nomenclature sometimes. We can look at sort of what happens specifically to the magnitude and the phase if we just look at a static phantom. That happens to be the data I had available. So here we can see for coil 1, this is the magnitude of the signal that's measured by coil 1. So where is the coil element placed in this image? On the top or on the bottom? I heard it. Say it louder. On the bottom, right? So the coil element must be on the bottom here because the signals are obviously the brightest. So I've got a second coil. I place that coil on the top of the object here, and I'm getting the best signals from the things that are closest and lower signals from things that are further apart. So this is a sensitivity issue. This has nothing to do with T1 or T2. This is a otherwise homogeneous phantom, right? Square root sum of the squares, I can combine these two images and get something that's very uniform in its appearance. Uniform as I would expect because T1 and T2 are the same throughout. What's a little bit less obvious is that the coil itself, the receiver field, if you will, can also color the phase of your signal. And that just has to do with the precise electronics that you've come up with and the impedance and dielectric coefficients of the tissues, some wavelength effects, whatever. Bottom line, the received signal will have an additional phase term on it that's spatially dependent, depends on a function of space, and could vary, in principle over the full range of plus minus, this should be plus minus pi, not plus minus 2 pi. So we know that this receiver field has a sensitivity and it has a phase. And we'll see those terms show up when we start working through these equations as well. Okay, so this is where we're headed. We have this idea that through the principles of reciprocity, that the flux itself is just the integral of the receiver coil's sensitivity and the state of the bulk magnetization. And then we need to we need to differentiate this with respect to time so that we can get back to having a voltage. And this is just Faraday's law of induction with a minus sign for Lenz's law. So this is procedurally what we're going to do next. Okay? Questions about sort of the hardware components and what we're trying to do? Yep.
Kind of a question. Why is it a dot product? Usually flux is a cross product.
Yeah, so why is it a dot product? I guess the answer I would give you would be, let's go back a couple of equations. So the question is, why is this a dot product? And I guess that what I would say is that you may intuitively expect that you would have a larger flux for a larger mx component if your receiver coil is sensitive to bx. Right? So this tells me how sensitive I am to either my x component of my B field, y component, or z component. And if for some reason I've designed a coil that has really poor bx sensitivity, then I won't get much flux from that particular component. So it comes in through a dot product. I don't know if that's exactly answering your question, but it maybe gives you some insight from this expression. Okay. So our task now, let me just get my slides down here a little bit. Our task now is how do we go from transverse magnetization to voltages? Let me switch it. Okay, so you've got, excuse me, you've got some of this in your slides already, but I'll go ahead and get myself started by writing down that voltage expression. So we know the voltage is a function of time was equal to minus the partial derivative with respect to time of the integral over the object. And this is where our B receiver field, which could have sensitivity that varies as a function of space, is dotted with the state of the bulk magnetization, which is also a function of space. It could be a function of time. And then that's over all of space, all of dr. And it may be important to point out that our B receiver field is not going to be a function of time. We assume that the electronics of the coil is stable and its sensitivity is not affected through time. We can expand this B receiver field out just component-wise, and so we would let our overall B receiver field as a function of space just be the sum of the individual components. So we have a B receiver field along the X component, along the I direction, and then I just want to write my other components as well. We want to look at this dot product ultimately and see which terms really matter. So I've got a Y component of my B receiver field along the J direction, and then I've got a Z component of my B field along the K hat direction. And you could do the same thing. We know what that looks like for the bulk magnetization already. So just substituting in, we know that our voltage is a function of time, still going to come from the time derivative of the integral over the object. And now we just want to make this substitution for the component expressions for both the B field of the receiver and the bulk magnetization. So I'll write a square bracket here, substituting in the different terms I have, or different components I have for my B field, my X component, my BR along the Y component, and my BR along the Z component. And that, of course, just gets dotted with the bulk magnetization component. So I need all three of them. So I have an MX component, which can vary as a function of space and time along the I direction. And then I'm going to carry that out for what's happening on the J direction and what's happening on the K direction. So then I have plus MY, which varies as a function of space and time along the J direction. plus mz, which can vary as a function of space and time along the k direction. And then close up the integral with a differential position output. We said just a second ago that the B field terms themselves are not functions of time. And so this simplifies a little bit when we go to take the partial derivative with respect to time, because we're really only talking about the magnetization components being functions of time. And so we're going to carry through the partial derivative all the way through this dot product. And we can leave our minus side out in front. We still have the integral over the object. And then I'm going to write out basically three terms. The first term is just the B receiver field along the x direction times the partial derivative of mx, which could be a function of space and time, partial with t, and that's all along the I hat direction, right? Carry out for the next two terms, and I have a plus B receiver field on the y direction times partial derivative of my, which is a function of space and time, differentiated with respect to time along the j direction. And then the final component is the B receiver field along z, the partial derivative times the partial derivative of mz, which is a function of space and time. That points along the k direction. And then closing up my integral with my differential position out. So just a little bit of algebra at this point to carry out sort of what's happening with this dot product. So a good question to ask right now is, which coordinate system are we in? So we've talked about principally two different coordinate systems, the laboratory frame and the rotating frame. Is this voltage signal in the laboratory frame or in the rotating frame? And how do you know? Any ideas? Lab frame. Why?
Because BR is in the
BR is in the lab frame. And as we've described it so far, even our bulk magnetization is in the lab frame, right? So right now we're clearly in the lab frame. And we've chosen our components to be defined in the lab frame. That's where I, J, and K are anchored, so to speak. We don't expect to have our B receiver field rotating at the Larmor frequency. We'll see in just a little bit that our transverse the components of our magnetization have a precessional frequency term with them, and that also tells us that we must be in the lab frame. We need to get away from that. We're going to get ourselves into the so-called rotating frame, but it'll take a few steps to actually do that. So let's think a little bit about what is the states of our magnetization. Now remember where we are in the experiment. Experimentally, we've done some slice selective excitation to excite some spins. We've chosen some timing parameters so that the contrast can develop. And now we've already turned on, say, our phase and frequency encoding gradients, and we're talking about capturing the signal very quickly. We're capturing that echo. And that echo, when we acquire it, tells us about contrast information as well as the spatial position information. This is what we're trying to understand better. So during the period of data acquisition, is that forced precession or free precession? Free, right? So forced precession is when the RF field is acting and pushing your magnetization to do something. Free precession is when we're hands-off, watching, observing, having contrast develop, or maybe listening in the case of recording an echo. So we could talk generally about the magnetization at this point. And our MX magnetization, which is a function of space and time, is proportional, say, to something like cosine gamma B0C. I'm not worried about the contrast information that's stored in here or anything. Right now I'm just saying that my MX component oscillates at a high frequency that's dependent on the Larmor frequency. Similarly for My, which is a function of space and time, it's going to be proportional, but it's out of phase with the X component, so it's a sine gamma B0T. And this really just falls out of the equations for free precession. I've left a contrast term out. I'm not worried about it right now. I just said they're proportional. We know this is a high frequency component of the magnetization, if you will. And then we have our mz magnetization as a function of space and time. And it's going to be proportional really to some sort of like initial condition, right? At the time at which I start recording my data, I have some state of my mz magnetization, and it's probably pretty constant while I'm acquiring data. Remember, when I acquire data, it takes a few milliseconds. So mz doesn't really do a whole lot. So it's proportional to some initial condition. Yeah, it's going to be trying to relax, but for right now, we can probably let that go. Now, these expressions here just really fall out of free precession. They're not actually the terms we care about. What we care about are their time rates of change. How are these things changing once we take a derivative? So easy enough. dmx dt is just going to be now proportional to a minus gamma b0 sine of gamma b0t. We could look at our my term, and it's going to be now proportional to something like gamma b0 cosine gamma b0t. And then lastly, we can look at dm z dt, and it's going to be proportional to just something like 0. Okay, so these two values here, these are relatively large, right? They have a gamma b0 in front, which is a pretty big term compared to something like 0. And again, they're really coming from the free precession equation. And this term here is really relatively small, right? We could have shown the exponential term and showing its relaxation, but as it doesn't really change very much with time over this very short observation interval. There's some assumptions here for now, but bottom line, let's say it's not really changing much at all. So what that means ultimately is that this last term in the expression that we had here is going to go to 0, right? Because we're saying the time rate of change of the z component is tiny relative to the time we're actually acquiring things. And so just to keep things a little bit moving along, I'm going to cross this term out here. Okay, we all agree that that term goes to 0. For your sake, I'm going to label this as equation A because we're going to need it a little bit later. Okay, I'm going to have to come back to it before too long. Probably some things to point out include that in this expression that we have now, there's just the two terms here, right? This voltage signal that we have, the received signal, it only really depends on mx and my, right? And that's true especially true at very high fields, right? Meaning that this term is large at high magnetic fields, right? If you were working with a Gauss field or milli-Gauss field, then you'd really have to reconsider whether or not this term was actually 0. But as everything we do is really at 1.5T and 3T systems, and these terms are substantially larger than any flux you could get from the Z. So this is the whole reason that we say our systems are only sensitive to transverse magnetization, because the flux generated by the Z component's tiny, right? It's tiny at high magnetic fields. It's not actually true if you go to, there are papers about, doing MR imaging with Earth's field, right? So if you get down there, then you have to reevaluate your assumptions and the things you've used in these expressions. Okay, so keep this in mind. I think I'm going to pop back to the slides for a little bit, but we're going to come back to expression A after we do a little bit more work. All right, maybe that's actually next. That's actually next. Okay. Okay, so remember what I said before. I said during signal acquisition, when we're recording and listening to our signal, this is the process of free precession. We're not perturbing the system. We're just trying to measure information that's coming out of the system. So at that point in time, during free precession, we can write out the state of our transverse magnetization, right? So it's going to depend on some initial condition, right? How much transverse magnetization do we have available to us at that point in time? And that could be a function of space. It'll certainly be a function of time. So I'll go ahead and write it as a function of space. I probably won't carry through with that. That magnetization, we know, during free precession is also going to decay. So, and it's going to decay because it's the transverse component as a function of time at T2. We need to include the precessional term if we're working in the laboratory frame. And so we know that there's also an e to the minus I omega 0 times time term. And then the last term that we may also want to take into account would be phase that was imparted on the spin system from the RF pulse itself. We can tip our magnetization into different parts of the transverse plane, and that gives us some intrinsic phase. And so we can map that out as e to the minus I phi RF. And so this is just an example of free precession during readout. I'm sure you caught it already, but this is just my initial condition. This is just my decay term. I always like you guys to understand what these different terms are. This term here is precession. And this term here is the RF phase. So it's a good expression for the state of our transverse magnetization. We can look at this component-wise. It's not so hard to do. So let's talk about our MX component. I'm just going to worry about it as a function of time. It depends on our initial condition, our MXY, which could be a function of space. Probably doesn't depend on time because it's our initial condition. And we're just going to care about the magnitude of it because I'm projecting I'm projecting this complex magnetization onto the real axis and then the imaginary axis. So I have it has a particular magnitude. It's still multiplied by some decay term, and T2 could of course be a function of space. And then to give me just the component that I care about, it comes through a projection, and so we just capture the cosine component, and it's going to depend on minus omega, which could be a function of space because we know how to manipulate our Larmor frequency by applying gradients. And then we still have to carry on with our the phase that could come from our RF. And that, in turn, could actually be a function of space, depending on how well built our transmit system is. We could have inhomogeneities in the RF phase that was imparted on our signal, depending on that system itself. Just doing the same thing then for our MY component. So MY is a function of time. Still has the same leading term here. It just depends on the magnitude of the transverse magnetization. It still decays as a function of T2, which could be a function of space. But instead of a cosine term, we obviously pick up a sine term here. That still depends on minus omega R plus the phase from the RF. So we're just writing out component-wise that first expression. Now the business comes down to we have to take the partial derivatives with respect to time of these expressions to understand their time rates of change. Pretty easily done. So dmx dt, what do we get for that? We have to do chain rule because we've got some different time terms in here. Oh, I screwed up. Sorry. There's a time right there. Otherwise, you wouldn't need chain rule. Okay, so don't miss that I added a time onto my omegas here. We had it up above, but now we're adding it on again. Okay, so let's take some partial derivatives of this. There's a leading term, which is just a constant. It's the initial condition term, so it's still mxy superscript 0, function of space, not time. And then we got to carry out a couple procedural steps here. The first thing we'll do is take the derivative of the exponential term. That leaves us with a minus 1 over T2 as a function of space. That's pre-multiplied on the exponential term, e to the minus t over T2. You can carry through the functions of space as much as you feel like writing them down. This is a pretty big parenthesis, so inside here we have to have a smaller parenthesis. Oops. Sorry. We need to have our cosine term, and that's going to operate on the terms that are just above there. The minus omega is a function of space times time plus the phase from the RF. So that's the first time derivative. And then the second one that we need to take into consideration, we keep the exponential term, e to the minus t over t2. And now we have an omega as a function of space that comes out in front. And this whole thing is just multiplied on a sine times minus omega, which is a function of space, plus the phase from the RF. And I need a big closing parentheses now, which just captures that the state of the transverse magnetization operates on this whole thing. Okay, just a time derivative of the different terms that are there. Quickly, we'll do the same thing for dmy. And what we find, oops, sorry about that. What we find, of course, is that we still need the bulk magnetization, or the state of the transverse magnetization out in front. Big parentheses. And then this term is going to look a lot the same, except for there's a sine instead of a cosine. So I still have my minus 1 over t2 multiplied on e to the minus t over t2. And now the difference is that I had a sine, I'm differentiating it, so my sine goes to I had a cosine, that's a sine, that's a cosine. That should be a sine, right? Oh, yeah, sorry, it's a cosine. All right, sorry. I did the time derivative of the first term, so I keep the second term. So this still looks like a sine of minus omega r times time plus phi r f. So now we need the second term. The second term, we're going to keep the exponential, if you will. I'll get a minus sign when I take the time derivative of this sine term down here. So I'll put a minus here, e to the minus t over t2. This is an omega r. And now I get my cosine term. And this is minus omega r times time plus phi r f. Close it up. Close it up. Okay? Yep.
Derivative of sine, negative sign, so the minus terms should be switched at the top and bottom.
So this term here, sine goes to cosine, right? And then when I differentiate, I get a minus from here. The minus omega comes out in front. Good? Okay. Okay, so geez, what do we do there? Well, there's a couple things to think about. And one of the questions is, how does 1 over t2 compare to omega of r? Okay, so if we look at our terms here, we basically have two different terms. We have terms that have something like 1 over t2 leading them, and we have terms that have something like omega r leading them. And you can see that in both expressions. The other stuff is mostly the same, an exponential t2 term and a trig term. So this seems like maybe a kind of funny question to ask, but they do have the same unit, so we could talk about their relative magnitudes. What's omega as a function of r? What's omega in general? What's that? It's like gamma times B0, right? So think big, megahertz, right? T2 is milliseconds, so it's something like 1 over milliseconds, so you're going to put yourself in the kilohertz range or something like that. So omega r is many, many, many orders of magnitude larger than something like 1 over T2. Again, because we're at high field, right? If we were at low field, you have to reconsider all of this, right? So, you know, that's another class entirely, right? So in general, we can say that omega r is going to be much bigger than 1 over T2, but specifically that's true at high field. So there's value in these expressions, right? Okay, so I'm going to label these guys as B, because we're going to come back to them a little bit later as well. And what it means is that these leading terms here, because these 1 over T2 terms are small compared to the omega r terms, this whole term can go to 0, and this whole term can go to 0. And so we're obviously, right, this is how derivations always go, right? You're looking for things to knock out. You're looking for big orders of magnitude so you can assume that something is 0 compared to something else. And that's the case here for the time rates of change of the two magnetization components. I want to go back and think for a second now. Remember, we're trying to figure out what does this voltage equation look like with respect to the B receiver field and the transverse magnetization. Here we understand now what's the state of the transverse magnetization after we differentiate it. Let's talk about our B receiver field too. So what does our B receiver field look like? We're just going to write this out. I think it was in the slides earlier, but we could write our B receiver field's X component is just equal to the magnitude of the B receiver's XY as a function of space times some cosine term. So this depends on the phase of the receiver. And we can similarly write down the BR for the Y component of the receiver's B field still has the same leading term, so it's still BR X Y times R. But instead of a cosine, we need to take into consideration a sine. And so it's the phi of the receiver field, which in fact be a function of space. And so you'll remember from before, oops, sorry, didn't close up my magnitude operator. We talked about this term, this leading term here as being the sensitivity. So we want coils with high sensitivity. We want to design the electronics such that our B receive field is as big as possible, right? And that has to do with the quality of the electronic components and the tuning of that circuit as to what kind of sensitivity it has. And then this second term here for both components was just something about the receiver phase itself. And we're going to come back and need these in just a second because you remember we broke this thing out we broke out that dot product as being the B field's X term times the MX magnetization, and then B receiver field Y component and Y magnetization, and we dropped the MZ magnetization. So we're going to need these in just a second as well. And these are equations C. Questions about where we are at this point? Okay. One more. I told you we were going to do a bunch of this. It's okay if I take this one down? I think some of you are doing this as quickly as I am, more quickly. We'll work through this one and then we'll get back to the slides for a little bit. Okay, so really what we need to do is from your notes, we need to plug B and should be C, but the two things that we just did, we need to plug that back into A. So hopefully you kept track of that. And so we'll end up with a really a rather long expression finally for the voltage signal. Let's see if I can get this flattened out a little better. Okay, so we're talking about writing out our voltage expression again. We know that it's minus the integral of the object. And just so you can plan ahead a little bit, this is going to take me 2 lines to write out everything. So depending on how you're using your own space. We've got a big bracket. And the big bracket contains the first B field term, which is the B receiver's field, the magnitude of the B receiver field. We need to take the cosine of that as well. So we have the cosine of the phase of the receiver field, which could be a function of space. That's just the B field definition that we had a second ago. That's going to multiply onto the available magnitude of the magnetization, which is mxy as a function of space, not time. And now that whole thing is going to operate on another set of terms that comes from the time rate of change of the bulk magnetization components. And that you'll remember, or you'll see in your notes, that it was an omega r dotted on e to the minus t over t2 to be a function of space. times sine of minus omega r times time plus the phase from the RF pulse itself, which could vary over space. Close up that bracket, and then I think that's all I can close up right now. Yeah, so this bracket's going to close when we get all the way down here because we're still integrating over the whole thing, right? So that's the first term. That's sort of the x term, if you will. And then we have to add to that then just the B receiver's magnitude, which could vary as a function of space. And we have to take into account the y component, which was sine of the phase of the receiver field as a function of space. Dot that with the state of the transverse magnetization, mxy, as a function of space, not time. It's an initial condition. That's all pre-multiplied on this very similar looking term from before, but it was a minus omega r. There must be a t in there. Right? Yeah. Sorry, gang. Should be a time in there. Anytime there's an omega, there's a time. We still have our decay term, which is an e to the minus t over t2 r. And then we have this last term, which is effectively the precessional behavior of the whole thing, which is a cosine times minus omega r times time plus the phase from the RF pulse. That closes up the cosine. This one closes up this basically precessional term, and then we close up the whole integral here, and I should probably need a dr on the outside there. Yeah, one
Why
second.
is there T? There shouldn't be a T there.
There shouldn't be a t on that? Oh, you're right, because that came out from the integral. Yeah, you're right. So scratch what I said about anytime there's omega, there's a t. Thank you. I don't mean to mislead. It's the worst thing we can do, right, is mislead. Okay, so that got a little clunky, but no surprise, trig is here to save the day, right? So you probably can't immediately see it, but you'll understand it in just a second. I'm going to take this phase term here. I'm going to just say we could let that equal beta, and that's the same phase term here, so that could all be beta. And now if I look closer down at my cosine term and the sine terms that are down here, what's inside is all the same. So let's go ahead and let this be, say, alpha, and let this be an alpha. I apologize. I think the parentheses get a little tricky to track. There's another one. Okay, like I said, trig is here to save the day. The trig identity that we're going to borrow from is that we know that cosine beta sine alpha is equal to, minus sine beta cosine alpha is equal to sine of alpha minus beta. And so the current expression has the form on the front end here, and we're going to collapse a bunch of these terms so we can just write it as a single sine term that's the difference of our alpha and beta. So that's our overall objective. If we make that substitution, then you guys can perhaps do it almost as quickly as I can, maybe faster. We still have minus integral over the object itself. And then this whole thing collapses down a little bit so that we have an omega, which is a function of space, times the B receiver field, which is also a function of space, the magnitude of the B receiver field. This is all that leading term, right? Or most of it's that leading term. Times the state of the transverse magnetization, which is just mxy, is a function of space, not time. And then we need a relaxation term, so e to the minus t over t2. And then the last thing is we finally bring in the substitution here so that we can just write that we have sine of minus omega as a function of space, t plus the phase from the RF pulse, which is a function of space potentially, minus the phase of the receiver, which is a function of space. And then we sort of just close things up with a differential at the end. So we've come a pretty long ways. We had a bunch of terms sort of zero out because of their low time rates of change, and now we've had some terms collapse because of a trig identity, and the expression gets a little bit more sort of tangible, if you will. I'm going to mark this as equation D because I think we're going to need it in a little bit. And then, I'm not sure if I'll write this all the way out, but we're going to need this expression in just a second. We can look at the different terms, right? We can say, okay, well, this is interesting. The voltage that we have obviously depends on the frequency. The higher the frequency, the higher the voltage. So that's one reason that high field scanners are useful, right? High fields generate higher voltages. The other effect was that we had more polarization, right? So higher magnetic fields are kind of an obvious thing in MR, although that's debatable in some sense anymore. Bottom line, the voltage that we receive depends on the frequency, depends on the sensitivity of our coil, it depends on the state of our magnetization, but the state of our magnetization decays over time, right? Even though we're only observing things over milliseconds, that magnetization's decay will affect the magnetization that we're actually recording. So T2 decay still enters in. Here we can see that we have a precessional term, right? So here's sine. This is the precessional term, meaning that the voltage that we get will depend on the frequency at all of the different positions, right? Those frequencies might be the same. Those frequencies might be very different. And then just some relatively constant phase terms. The phase from the RF pulse itself and the phase from the receiver coil. The receiver coil adds a phase to the recorded signal. So this is a useful form of this particular expression. It turns out we can also, perhaps not surprisingly, rewrite this. If you just remember that minus sine of, say, alpha, not the same alpha, but just n alpha, that's just the same as the cosine of alpha plus pi over 2. We can rewrite the same expression, and rather than writing it as a sine, we can write it as a cosine. I'll save you guys maybe the grief of watching me write every term, but this just ends up looking like a cosine minus omega as a function of space times time, plus the phase in the RF pulse, minus the phase of the receiver, plus pi over 2, plus pi over 2. And so this is just another way, and you'll see why that matters later, but it's another way of writing that same expression, just a phase-shifted version of itself. And so I'll call this expression E here. I didn't fill in the whole thing, but you'd have a, let's just do it. So you have a V of t here minus the integral over the object of omega r dotted on the receiver field dotted on the initial condition, right? And then we add a relaxation term as the last term, e to the minus t over t2 r. And really the thing to remember here, this was just all trigonometry and algebra really, but there are there's two slightly different versions of this voltage equation. But at the end now, we understand how our voltage that we record, pick up on our coil, is related to the receiver system's B field, the sensitivity of that coil, as well as the state of the transverse magnetization with some precessional term and some phase terms as well. Okay, so I think that gets us back to our slides. Yeah. So what we have at this point is a really high frequency signal, right? It's pretty high in magnitude, but it's also very high in frequency. The really interesting information is not in the high frequency. The high frequency is just the carrier signal. The interesting information is in the sort of kilohertz range that was the spatially encoded information that the gradients added to this carrier frequency term. And that'll be one of the next things we have to dig into. Okay? All right, let me see where we are and where we need to get. Why don't we take, just because it's a natural point, why don't we take a few minute break right now, and then we'll come back for like the last kind of 40, 45 minutes. We'll see how, if we don't get all the way through this, that's fine. We can pick it up on Wednesday. Okay? So quick break. Yes, sir.
I didn't quite hear about the BR. What is the BR?
It's a little, the way I think about it, it's the B field generated in a receiving coil.
Okay.
So you have a coil, and if that coil is really sensitive, then it will generate a bigger B field because of the bulk magnetization. If the receiver is poorly constructed, it has a low sensitivity, the B field generated in the coil will be low.
So this is just an extra B field beside the B0.
Yeah, it's specifically the receiver's B field. So the receiver is the coil that we place somewhere, right? And that coil will end up with a flux because of the bulk magnetization. You'll end up with a current in it, and it will generate a field.
Okay.
And that falls out of what's called the principle of reciprocity. For me, it's a little bit easier to sort of understand that if my coil has poor sensitivity, then I shouldn't measure my magnetization very well, so that my voltage will be very low.
Okay, and the receiver coil is a multi-channel coil placed at the different positions, and all these coils it generates a B.
They all have their own B receiver field.
Oh, each receiver coil has its own B field.
Yeah.
And this is actually the net effect of all this B field.
This is just what's happening in a single channel, a single coil. Our whole system is usually many channels, many
And
small
you need to measure all these different B fields.
Yeah, and then add them all up. Effectively, you get a flux or a voltage for every coil, and then we.
Oh, this is for one coil. This is for
one coil.
One receiver coil. Oh, okay. And another question is, among all these voltages and signals, what is the actually you receive the signal? What is the actual signal you receive? Is it SK, the case?
Well, I mean, it depends what you mean. The thing that you are able to detect is a flux in the coil. The flux in the coil is measurable as a voltage.
Yeah, but you didn't actually acquire the voltage. You actually acquire K-space.
No, you measure the voltage. First thing you measure is the voltage.
Okay.
And then once you have the voltage signal, how does this get us to K-space? You have to know how to interpret that voltage signal. The steps we're working on right now is understanding how is that voltage related to the magnetization, and then how does that voltage tell us something about K-space.
Oh, so in the scanner you actually measure the voltage?
It's the very first thing. When you as a researcher get the data, you'll get the K-space data. But what I want you guys to understand is everything that happened before we had K-space data.
Oh, so the data we actually acquire is the K-space data.
The data that's recorded on the computer is the K-space data. But there's a lot of stuff.
It is generated from the voltage.
Yep.
Oh,
exactly.
I see.
Yeah. No, it's a good question. It's a good question. All right, 2 seconds. Let me get a drink. Alrighty, guys. So I had a really good. I'm sorry, I'm terrible with names. I had a nice meeting with you. Sorry, your name? Sen Ma. I know the names once I get them. So I had a nice sort of discussion with Sen there about sort of where we are and what's going on. So I think I want to sort of recap what that was about. What are we talking about? Well, as a researcher or whatever, the data that you're really going to be dealing with is K-space data. Okay, that's the data that's written to disk, and then a Fourier transform gets us back to image space. And oftentimes in research, we want to deal with the echo data because we can do a few things with that we can't exactly do with images. And frequently we refer to the K-space data as the raw data. It's not the raw data. The raw data is all the way back to a voltage, right? So the first thing this system does is measure a voltage, right? You've got a coil. You have bulk magnetization creates a flux in a nearby coil. That coil then has a current or measurable voltage induced in it. And that's the first thing that's recorded by the digital acquisition system is that voltage. What we're talking about, what we just talked about was how does the state of the transverse magnetization influence the characteristics of that voltage signal, right? If I have no transverse magnetization, I have no voltage. If I have a high frequency state of magnetization because I'm a high field, then I have a highly oscillatory voltage signal. It doesn't just depend on the state of the transverse magnetization, it also depends on the state of the receiver system. So if you have a crummy receiver and your B receiver field is poor, then you won't detect very well a voltage, right? Now it's a little confusing. What's this B receiver field? It falls out of this principle of reciprocity, but the idea is that your transverse magnetization induces a current in that coil. Currents in a coil produce a field. How good of a job your coil does at transforming the transverse magnetization into a field effect is related to the sensitivity of that coil. If that coil is not very, very sensitive, then a lot of transverse magnetization hardly makes your coil budge. You hardly get any detectable voltage. It has poor sensitivity and consequently a very poor B receiver field. Now that's happening in the individual channel, right? We talked about having 2 channels on the front, 2 channels on the back, or multiple head coils around your head. Everything we're talking about right now is just at the single channel level. Once you've gotten the voltage from that channel, and then we go through some other steps to finally get to K-space, you'll have K-space for one channel. And now you'll get the K-space from all of the other channels, and then there's various ways that we can combine that information. The easiest of which is a 2D Fourier transform to image space, and then a root mean sum of squares of all of those images together. That gives you pretty uniform weighting. We'll show you some other details about that final step there. So what we've come to understand hopefully right now is how the B receiver field, which is our coil, and the state of the transverse magnetization influences this voltage that we recover. But the voltage itself is not a useful signal to us. We have to act on that voltage signal to get it eventually to be a K-space signal. And that's the steps. We'll see how far we get, but that's our goal right now. Okay? Questions about procedurally what we're trying to work through? Clear as mud? Okay, so what we just hopefully agreed on is that we have some understanding of how the transverse magnetization gives us a voltage signal. That's not actually quite enough. Voltages are just time signatures, right? The voltage is just oscillating as a function of time. What I really want to know is I want to know how much bulk magnetization do I have and where is it in the transverse plane, right? To figure out where it is in the transverse plane, I have to use what's called phase-sensitive detection, okay? We're going to look at that voltage signal. We're going to act on it in slightly different ways so we can actually determine if the transverse magnetization at the time we recorded it was pointed along X or pointed along Y or pointed along minus X or pointed along minus Y. And that's useful for us because the phase of our signal is actually a useful thing in MR. There's information in the phase of the signal. What this means is we have to be able to take our voltage signal, act on it through the process of phase-sensitive detection, and that will lead to what ends up being the next step of how we recombine these 2 signals into a complex signal. You have to have a complex signal to talk about the state of the transverse magnetization, because mathematically it's easy to talk about having real and imaginary components, and we can sort of just couple things together that way. That'll be the third part of today. Again, if we get there. So what I want to talk about right now is this process of phase-sensitive detection. Again, try to give you some intuition for why this is a useful thing, and then we'll look at the math of how it bears out. So where are we in the process? Well, we understand now that we get a voltage in our coil, and that voltage just gets, say, sampled by a digital sampling system and recorded to a computer. Okay, fine. Now what? Well, the next thing is that voltage signal. We're literally just going to multiply it by either a cosine signal or by a sine signal. And importantly, the cosine signal is going to be at the Larmor frequency, and the sine signal is going to be at the Larmor frequency. And you're going to see what effect that has. We'll show you in a second what effect that has on this voltage signal. Through this process, basically a phase-sensitive detection, we can get ourselves into sort of individual components of the transverse magnetization, and we'll finally get this complex S of t signal. So you'll see, this will be a complex signal. It varies as a function of time, but it tells us about both the magnitude and the phase of the transverse magnetization. And then we're just really a step away from getting into K-space, which will be the next thing. So why do we go through this process of phase-sensitive detection? There's a couple different reasons. One is that this method, this phase-sensitive detection method, can extract a signal with a known carrier frequency from a really noisy environment. And we know these systems are really, highly engineered. We know what our carrier frequency is. It's much easier to pull the signal out of a system if you know the carrier frequency, then you can use this PSD method. And it basically just consists of multiplying the voltage signal by a reference signal. We know the reference signal, we know the Larmor frequency, we know what to use. And then using what's called a low-pass filter to remove the high frequencies. So a low-pass filter will let the low-frequency stuff through, and it'll shed the high-frequency stuff. Mathematically, we'll just cross out a term, but there's a whole art to filter design involved here as well. There's different ways of thinking about this. This effectively reduces, what are sometimes called unnecessary problems associated with high-frequency signals, process stages that would come later in this whole sequence of events. One of the really useful things that comes out of this is that by using two so-called orthogonal PSDs, that is a cosine and a sine phase-sensitive detector, we can get so-called quadrature detection, and this results in a complex S of t signal. And again, the advantage or point of a complex signal is to tell us where is the transverse magnetization in the transverse plane. That phase information is useful to us, so we want to decode it if we can. This whole method is also called a lock-in amplifier. It's used in a lot of different sort of signal detection methods that are when you have a known carrier frequency, like in AM radio. Okay, so a little bit more carefully, what does this look like? Our voltage signal is going to come in. We're going to multiply by either a cosine or a sine, and then we're going to combine both of these signals, and you'll see how, into this complex signal. This phase-sensitive detection process inside that PSD box is just this, and you'll see it literally. We're going to take our voltage signal. We're literally going to multiply it by a reference signal, and then we'll apply a low-pass filter. You'll see there's going to be two components that we're dealing with. One's going to be really high frequency, and one's going to be pretty high frequency. And we'll knock out, actually it's going to be low frequency and really high frequency. And we're going to knock out the super high frequency stuff and be left with this lower frequency signal. In doing so, we're actually going to transform ourselves from the laboratory frame to the rotating frame. I've said it a lot of times in this class about demodulating the Larmor frequency. And that's what this PSD, that's what the low-pass filter is going to do. The low-pass filter is going to get rid of or demodulate the carrier frequency. And in doing so, we've made that transformation from the lab frame to the rotating frame. Gotten rid of that 64 megahertz business. So that'll be part of this, and then you'll see we'll combine signals after the two different phase-sensitive detectors in the end. This just, if you're not familiar with sort of digital filters, this is an example of a low-pass filter. And the idea is that the filter has the effect of multiplying the frequency spectrum by different amplitudes. So we retain the amplitudes of low frequency signals. This rolls off at some intermediate frequency range such that the amplitude of very high frequency signals is knocked down. This is the example of a low pass filter. If you flip this thing over, you can have a high pass filter. You heard Dr. Sung talk a little bit about baseband filters. We don't have to know a lot about filter design. Just remember that we can multiply or apply a low-pass filter in the frequency domain such that we knock out really high-frequency stuff when it's a low-pass filter. And you'll see mathematically we'll just cross out a term. Okay. Questions about where we're headed? All right. I should have done this already. Sorry. keep your notes handy because we'll be starting off with some of those expressions that had applied labels to. Okay, I'm going to do myself a favor and perhaps yourselves as well. So going back to this expression that we had that we labeled as E, it was one of the last things we did where we had an intermediate length voltage expression that had a cosine dependence. So from E, I'm going to go ahead and I'm going to make a substitution here for a bunch of things so I don't have to write them every single time over and over. So I'm going to let psi stand in for omega r. It's just that sort of leading term in that expression, which was dotted with the B receiver field, which was dotted with the state of the transverse magnetization, which was dotted with a decaying exponential term. So I'll be glad to not write that too many more times. What we're going to do is we're going to do the first PSD, the first phase sensitive detector. And we're going to start with the 2 cosine omega 0 t operator. And then remember, of course, that omega 0 is just equal to gamma B0. So we know pretty precisely how to generate this reference, what we call the reference signal in the phase-sensitive detector. So going back to E and using my substitution here, you have something like 2 times the voltage times cosine omega 0 t. So just multiplying literally by this function, right? And we're going to multiply both sides, of course, because that's the fair thing to do. So then we have 2 times the integral over the object times psi. There we go. That saves some time. Times cosine of a bunch of things that look like omega r times time plus phi of the RF pulse minus phi for the receiver. And remember, I did that funny transformation, so I'd have a cosine, so I ended up with this pi over 2. And then I did, like I said I would, I multiply this whole thing by cosine omega 0 t. I probably should have written my dr before the cosine term, but it doesn't matter too much. Saving myself some time again, too, I'm going to go ahead and let this whole thing here just be an alpha, and let this whole thing here be a beta, this little thing here be a beta. If that's confusing, I apologize. We used an alpha and a beta before, but these are new alphas and betas, just trying to streamline things a little bit. So no surprise, we'll bounce off of a trig identity here. So we know that 2 cosine alpha cosine beta, which is the form of this integral expression right now, that's just the same as cosine of alpha plus beta plus the cosine of alpha minus beta. If you actually remember that, you're a step ahead of me. We'll use that trig substitution here, and then we can really talk about what's happening to some of these terms. And so we just end up with 2 times the integral over the object. There's a bunch of things tucked into that psi still, and that's going to be times cosine of alpha plus beta, using the substitution I had before, times dr. And this is just the first term from this trig substitution, so now I need to have basically a very similar looking expression, which is 2 times the integral over the object of psi dotted on cosine of alpha minus beta. Okay, so let's look at this, specifically look at this alpha plus beta term. So alpha plus beta, that's just equal to minus omega r, just going back to what the original definitions were, plus omega 0 times time, plus the phase from the RF pulse, which is varies over space, minus the phase from the receiver, which can vary over space, and then I still have that plus pi over 2 hanging out. These two terms right here, I can say that that's really a delta omega term, right? I have some carrier frequency term which showed up from this multiplication that we just did with the 2 cosine omega 0t. But I also still had this effectively spatial frequency encoding term where my omega could vary as a function of position. And I'm differencing the two of those. This term here looks something like omega 0, but it varies as a function of space. So the difference of these two things is just like a delta omega. And so I can write that as a delta omega as a function of space times time. And I still need the phase for my RF minus the phase for my receiver plus 2. And so interestingly, this term right here now, this represents a low frequency demodulated signal. And this puts us in the rotating frame for this particular signal. Rotating. Okay, so that was just what happens in the first cosine term. Now I have to look at what happens when I difference my alpha and my beta. So when I difference my alpha and my beta, things don't turn out quite as nicely. I get a minus omega r times time minus omega 0 times time plus phi rf as a function of space minus phi receiver as a function of space. Probably I need a pi over 2 in there too, right? Alpha, this is alpha minus beta. Yeah, so there should still be a plus pi over 2. Sorry. So the real difference about this signal here is at the end of the day, this is really, approximately equal to minus 2 omega 0 as a it won't be a function of space, it's approximate, times time, plus my phase terms. I'll talk about these terms in just a second. So plus my RF phase term minus my receiver phase term plus pi over 2. And the thing to notice here is that in differencing these two signals this time, I ended up with a very high frequency signal, right? So this all goes inside some cosine term up here, but I'm taking the cosine of something that's twice my omega 0. Okay, omega 0 is a very high frequency term. This is twice that frequency. The other term that we ended up with here, this is a very low frequency term, right? We got rid of the carrier frequency. We got rid of that baseband Larmor frequency. And so this term here is very high frequency. And this is where that low-pass filter comes into place. And so we can low-pass filter to remove it. Oops. So again, we're looking at the significant difference in orders of magnitude between this alpha plus beta term versus this alpha minus beta term. And the bottom line is because they're so different, we can now apply a low-pass filter to get rid of the really big term, the really high frequency stuff, and just keep and retain the low frequency stuff. Okay? So this term is going to stick around, and that term is going to go away. And so where does that leave us? Well, it leaves us with what we'll call the voltage signal that's been phase sensitive detected, the PSD signal. We use the cosine reference signal to do it, so we'll call this the VPSD and superscripted with C for the cosine signal. It still varies as a function of time, of course. It's still a time varying signal, but it's a little bit simplified in its overall terms. If we go back, well, here, I'll write it this way first. So we have integral over the object, right, of psi times the cosine of, in this case, alpha plus beta dr. And that seems, sort of simple enough, but what we've left out is a number of substitutions that give us a little bit of insight about what this expression actually means. So now I'm going to finally go back into plugging back in what is psi, what's alpha, and what's beta. So I'll write this out. You may be able to do it from your own notes almost just as easily. We can leave an omega 0 way out in front. We'll integrate over the object still, no surprise. We bring back in the receiver's sensitivity. We bring back in the state of the transverse magnetization. We bring back in that e to the minus t over t2 decay term. And all of that operates on cosine alpha plus beta, which in this case now looks like minus delta omega r times time plus the phi from the RF pulse, which varies over space, minus phi from the receiver, which varies over space. We still have that little pi over 2 that we added in a while ago, so we'd have this thing looking like a cosine, and we can button it up. Now, there's a lot going on here, right? This tells us that our voltage depends on the magnitude of our frequency. That's a good thing. This is pointing out again that high field systems generate larger voltages, and that's useful for us. And the signal that we detect at a particular point in time is the integral from the whole object. It's every state of magnetization in the whole object. Depends on the sensitivity of our coil. Depends on the state of the transverse magnetization, which is going to be decaying as a function of time. And here's where things look a little bit different finally, is the signal depends on delta omega. We're going to have to come back and talk about this term in a second, but it depends on how different are you from the carrier frequency. And we have differences because we've applied gradients. We use gradients to give us a distribution of spatial frequencies or distribution of frequencies, and that shows up in this term here. It's this term here that in just a little bit this is really related to spatial encoding. It's going to be related to the gradients, and it's then going to be related to k-space. So this is the really important sort of spatial frequency encoding term right now. It's going to show up a little bit later. And then we just have some phase terms that go with it. Now, what we can't tell with this signal alone, this is just going to be a voltage that's oscillating as a function of time, right? So we can't actually tell from this signal alone if our transverse magnetization is going clockwise or counterclockwise, okay? So if I wanted to know, is MXY going clockwise or is it going counterclockwise? If that's the question, I do want to know that because I want to know what's the phase of my magnetization, because that phase information is, in some applications, more valuable than the magnitude information. But to do that, I need another phase-sensitive detector. I need my phase-sensitive detector using a sine, okay? I think I left it out of the notes, but the bottom line is you're going to come back up to this expression here, and instead of multiplying by the 2 cosine omega 0t, you're just going to multiply by a 2 sine omega 0t, and you're going to have different terms show up, and you're going to be able to high-pass filter one of those terms away and end up with 2 components, two different ways of detecting your magnetization. And the way you could sort of have, picture that is you're basically trying to figure out what's not just the magnitude of your voltage, but what's the phase. And that gives you insight to the phase of your transverse magnetization as well. Okay, so we're there. We're not all the way there, but we can probably carry through with the algebra to multiply through by the sine in the same way, knock out a term, and now we would have 2 different voltage signals coming from the same information. That's the kind of trick here, kind of interesting. You take that same raw voltage signal and you're just multiplying it by a different carrier frequency, sine or cosine, and then you're low-pass filtering it the same way. That'll give you 2 signals that we could use. Knopf?
Right, I'm going to elaborate a question, but what happened to the 2, or should that be a half?
I've got my 2s here, my 2 carried through here. Probably there should be a 2 here. Yeah, I won't promise that I didn't lose track of the 2.
It's in your Chicanon too.
Right. Sorry, you're right. Yeah. So that's yeah. Okay. Sorry, and that's the whole reason we put the 2 in, so we don't have to carry around a bunch of halves later. And so the 2, the 2 that shows up here basically disappears when you make this trig substitution here
So the
from the right hand side.
BPSEC, is it 2 times BT both sides, or is it just BT?
Oh, I see. Yeah. So you're saying where does this 2 end up? Yeah, it could end up in the front here. The interesting thing, and this, it's easy to double check or to be positive about that. When it comes to MR, we actually like we're not. It's my advisor used to say you're not counting photons, right? This is not a PET detector where you're really counting events. Here you have a voltage signal, and the voltage that you get depends on a ton of things, including like the sensitivity of your coil. So there's in MR, unfortunately, there's a scaling effect that we carry pretty imprecisely, because the scaling, unfortunately, is not actually meaningful to us. Never mind all the amplifiers and preamplifiers in this whole receiver chain. So that's one way of excusing having lost track of the 2. I have other ways too. I'll go with that. Okay, so a lot of work. It's 1:45. Let me just maybe make a couple comments, and then I'll let you guys roam free. This is the idea. The next step would be what's called quadrature detection, right? We're still trying to get from this voltage signal. We understand, okay, fine, we have a voltage. How do we get to a K point, right? And so the idea is we would go through the procedure we just went through with a sine reference signal, and we would end up with these 2 voltage signals. I won't work through the steps right now. I think if I did, that would drive me mad. Is it true? Oh man, it's so tempting. Okay, it's been a long day. It's really nice outside. So we won't go through this right now. We'll come back on Wednesday, and we'll have time to do this. It'll take the first 10, 15 minutes of class or something like this. But the bottom line is we would multiply through by this other sine detector. And now we basically just have 2 different ways of measuring information that's stored in our voltage signal. We can combine that through a process of mixing. It's just adding those 2 signals back together, making one the real signal, making one the imaginary signal. Then we'll end up with an S of t signal, which is actually an imaginary signal in the rotating frame that tells us about the state of our transverse magnetization at the point that we're recording it. And with that, I'll go ahead and wrap. And we'll come back with this last page of notes and start off talking more about K points and how K points report back to us information about our underlying object. So hopefully tying back again one more time, gradients and K-space and time and all these crazy signals. Okay? All right. Dismiss.